Yeah, I have a question regarding the multiple bits per cell memory technology. That seems like black magic to me that may violate information theory, and I'll explain a little bit. When I was at Intel, I was the apps engineer responsible for a new ROM technology that could save 2 bits per cell. And the idea was the normal ROM has either a little tiny transistor that's there or it's not, that's 1 bit. But these ROMs had a little tiny transistor or a medium-sized transistor or a large transistor, and the circuitry could determine which of those 4 options it was. That means in order to save 2 bits, you had to have each transistor be 3 times bigger than it had to be if it only had to save 1 bit. And the chip was actually larger than it had been if they hadn't been using multiple bits per cell. The analogy here is that if you're saving an analog charge, your capacitor has to be so big that your sense amps can detect the difference between 4 different levels instead of simply on or off. And that would seem to require a much bigger transistor than you would otherwise need. So where do you get that extra magic?
So the analogy, the correct analogy is this bottle. It can either be full or empty, that's binary, or it can have 3 levels, 4 levels of fullness, which I look at it and I know what it is, and that means 2 bits, or 8 levels, and so on. So the transistor is the same size. It's just how many electrons you're storing in the floating gate.
Well, why not make a smaller transistor then? If you only need to save 1 bit, you wouldn't have to have those intermediate thresholds.
Because whatever you could do with one bit transistor, I'd like it to be 2 bits. The smaller it is. One of the problems for non-scaling is there are not enough electrons left. That if you split them into different quanta, 20, 40, 60, and 80 electrons, because of infringing fields from capacitances around, your signal-to-noise ratio is no good. But so long as you can identify, in principle, you can have 1 electron per state.
So first of all, the transistor size, you want to make it the smallest possible. Done. So the question is, given that, what do you do? In the case of the charge sensing, what you're losing is you lose signal level. The more level you divide, the less signal you get. But then that's where the system flash comes in. The breakthrough is by using all the fancy Hamming, all this new code that you can sense, you can differentiate between very small level. So that's the difference.
There's speed too, right?
Yes.
Well,
no free lunch.
Yeah, but for the application of a secondary storage, you have you're trading off the access speed of the memory versus the processing speed of the controller. And there's a lot of things you can do to trade off. And that our challenge for NOR is we need to get to a first access of 50 nanosecond. For NAND, the first access is 15 microsecond. So there's a big room they can work with for speed.
So we have another question right